Hi, I'm Mark Barsamian. In this video, I'll be discussing an introduction to sets. This material is from our book, Millman Parker, Geometry, a Metric Approach with Models, 2nd edition. More specifically, it's from section 1.2, pages 3 to 4. The corresponding homework is this short collection of 2 exercises from section 1.2. Section 1.2 begins with some definitions of basic set terminology on page 4. First of all, the definition of subset. This symbol, spoken T is a subset of S, means in words that every element of T is also an element of S. With universal quantifier more explicitly stated, we would say it this way. For every x in T, x is an element of S. Or if we want to express it as a universal conditional statement, for every x in the universal set, if x is an element of T, then x is an element of S. Now in this universal conditional statement, we have this green statement, x is an element of T, which is called the hypothesis of that conditional statement. And this statement, x is an element of S, which is called the conclusion of that conditional statement. And the thing in front, the blue phrase, is the quantifier. Now we can abbreviate the statement in symbols. If we do that, the quantifier gets abbreviated this way. The upside down A is spoken for every, and this epsilon is spoken in. So this underlined statement is spoken for every x in T. Now the thing in parentheses is called the predicate. Now writing the universal conditional statement in symbols looks this way. For every x in the universal set, the predicate then is this entire thing in parentheses, which is a conditional statement. The x is an element of T is the hypothesis of that conditional statement, and x is an element of S is the conclusion of that conditional statement. Note that some books use the symbol like that for subset. If you were in Math 3050 using the book by Susanna Epp, the discrete math book by Susanna Epp, you would have seen this symbol used for a general subset. Set equality is defined this way. This symbol, T equals S, in the case where T and S are sets, means the following. Sets T and S have the same elements. Another way of saying this is that regardless of the element X chosen from the universal set, the statements X is an element of T and X is an element of S will always both be true or both be false. Now, I feel that's the simplest way to define set equality. A very common way of defining it is the way that it's defined in our book, using subset terminology. So our book says that to say that two sets are equal means T is a subset of S and S is a subset of T. Now that's true. That means the same as this stuff that I wrote up here. I prefer my definition because it doesn't use the idea of subset. It just talks about the fact that the sets have the same elements. But some people are comfortable with this, so you'll see both presentations. The empty set is denoted by this symbol, which is spoken phi or phi, the Greek letter. It's the set with no elements. Now, it's a fact that the empty set, phi, is a subset of every set. That is, for every set S, phi is a subset of S. This fact is proven in courses like Math 3050. I won't prove it here. We'll be dealing with operations on sets. The first one we'll discuss is the union of sets A and B denoted by this symbol. This symbol in the middle there is referred to as the cup symbol. So this typeset collection of symbols could be spoken A cup B, but it's A union B is what we'll refer to it by in talking about sets. The meaning of that symbol is this. This symbol stands for a set, the set of all x's in the universal set such that x is in A or x is in B. The intersection of A and B is denoted by this symbol. Now that upside down U in the middle is referred to as the cap symbol. So this typeset collection of symbols could be spoken A cap B, but we'll refer to it as A intersection B when talking about sets. And the meaning of that symbol, the meaning of the intersection of A and B is it's a set. The set of all x in the universal set such that x is in A and x is in B. We say that sets A and B are disjoint to mean this. The intersection of A and B is the empty set. The complement of A in U is denoted by this symbol, A with a superscript small letter c, and it means this: the set of all x's in U, the universal set, such that x is not an element of A. So you can't talk about the complement of a set without having an idea of what the universal set is. That is, as illustrated in this picture, the complement of A is all elements of the universal set that are not in A. And finally, set subtraction. This phrase, B minus A, denoted by this symbol, B minus sign A, in the case where A and B are sets, means this set, the set of all x's in the universal set such that x is in B and x is not in A. A more abbreviated description of this is the following: B intersect A complement. We can illustrate the set difference with a Venn diagram. Let's go on. Example 1. This is similar to one of your homework exercises, 1.2 number 1. Prove that if A is a subset of B, then A union C is a subset of B union C. Now this is similar to a book example. Now the book example is very densely written. There are not line breaks in the proof. There's no discussion of why the proof looks the way it does. That's typical for a math book at the level of our book. That is a kind of upper level undergraduate book that assumes that you have had a substantial introduction to proof in the past. Now in our course, you're supposed to have had an introduction to proof. Some of you may or may not have had as much as you need for this course. Even if you have had an introduction to proof, I think it's good in this course to review the ideas of how do you structure a proof. So for those of you who have never studied introduction to proofs, this will seem like a very brisk introduction. And for those of you who have had significant introduction to proofs, this will seem like an unnecessary review. So it'll be too fast for some of you and too slow for some of you. But that's just the way it's got to be. So first of all, recall from the previous courses a few things. First of all, the statement above is what's called implicitly quantified. That is, the statement is claiming to be true for all sets A, B, and C. We can write the quantifier explicitly for all sets A, B, and C. If A is a subset of B, then A union C is a subset of B union C. And as I said earlier in the video, the for all quantifier is called the universal quantifier and can be abbreviated this way: upside down capital A, spoken for all sets A, B, C. If A is a subset of B, then A union C is a subset of B union C. Also recall the form of a conditional statement. If P, then Q. The statement P is called the hypothesis. The statement Q is called the conclusion. And as I mentioned earlier, a conditional statement with a universal quantifier parked in front of it is called a universal conditional statement. So what we have here is a universal conditional statement. Also recall from earlier courses, if you had an introduction to proof, recall that a universal conditional statement can be proven with what's called a direct proof. That is this form. You start with statement 1 saying, suppose that A, B, and C are sets such that A is a subset of B. So you start with introducing a generic collection of elements that are described by the quantifier and also that satisfy the hypothesis. That's how the proof begins. Now the proof ends with, therefore, A union B is a subset of B union C. So you end with the conclusion of the universal conditional statement. So there's the conclusion of the universal conditional statement. It gets put down at the very end of the proof. There's the hypothesis of the universal conditional statement put in line 1 of the proof. So line 1 of a direct proof contains an introduction of elements as described by the universal quantifier and satisfying the hypothesis. That's all that goes in step 1, but all that stuff needs to go in step 1. And the very last statement of the proof has the form, therefore, the conclusion is true. So we have a frame of a proof. We have these two statements that bracket the proof, the beginning and end of the proof. That's how the proof has to begin and how it has to end. Now notice that the first term of the proof contains the term subset. Spoken is a subset of. So the first statement of the proof contains that term. This is a defined term, the definition we discussed earlier. The only thing that can follow that statement is a new statement that expresses what that subset symbol really means. That is, we have no choice about what statement 2 has to be. Statement 2 has to be this. For all x, if x is in A, then x is in B. So we have taken that symbol and we have expanded it and written here what it actually means. So we've replaced this abbreviated symbol with a less abbreviated sentence that expresses what it really means. This is called unpacking the definition. We're allowed to do what we did because we used the definition of subset. The definition of subset says that this symbol means all this stuff. Now, this is an example of this general practice in writing proof. If you're given a statement that involves a defined expression, then you must follow that statement with a new statement that is the unpacked version of the defined expression. So in going from statement 1 to 2, we have unpacked the definition. So we have no choice about that. Let's go on. Now, realize that the final statement, the one numbered with just an asterisk because we don't actually know what number statement that's going to be, that also contains the defined term, the subset symbol. So there, the final statement of the proof contains the subset symbol. The only way to get to that statement is to have preceding it another statement that expresses what that asterisk statement means, but in unabbreviated form. That is, we have to precede statement asterisk with this statement. Now we don't know what its number is going to be either. It's going to be the second to last statement of the proof. And realize that what we've done here is we've taken this abbreviated symbol and we have written what it really means in unabbreviated form. So the idea is, if the goal is to get to here, then the only way to get to that final statement of the proof is to first get to here. And then once you get to this statement, double asterisk, with some justification, we don't know how we're going to get there. Once you get to there, then you're allowed to write the final statement of the proof using, this should say double asterisk here, using double asterisk statement and the definition of the subset. So we have gone from an unabbreviated sentence here to an abbreviated sentence using the definition of subset. So in going from the second to the last statement of the proof to the last statement of the proof, we are doing what's called packing up the definition. So this is an example of the following general practice. If the goal is to prove a statement that involves a defined expression, that is, an abbreviated expression, you must first prove a statement that is not abbreviated. So our goal was to get to this abbreviated statement. So the only way to get there is to first prove this unabbreviated statement. And then you get to the last statement by using the definition of subset. That is, you pack up the definition of subset. So we have no choice about what has to go here in the second to the last statement of the proof. Let's go on. Now realize that statement double asterisk is a universal conditional statement. There's the universal quantifier for all y. There's the hypothesis, y is an element of A union C. There's the conclusion, y is an element of B union C. Now remember that universal conditional statements are proven by direct proofs. In fact, we're building a direct proof of a universal conditional statement. Now within our proof, there's this statement that itself is a universal conditional statement. So it's going to get proven by a little direct proof of its own. So there's the frame of the direct proof. The direct proof for statement double asterisk. So only after we have proven the statements bracketed here in black, only after we've done that will we be able to say this blue statement that was our goal. So we have to get through this black proof within a proof in order to get to this statement that we want to get to. So we have no choice about needing this black frame of a direct proof in order to get to the blue circled statement double asterisk. Now let's go on noticing some things that have to be dealt with. In our new frame of a direct proof, those statements that have to be there in order to justify the double asterisk statement, in that frame, in that statement 3, there is a defined expression, A union C. Well, that's a defined expression, so we have no choice about what must follow statement 3. We must unpack that definition. So as of statement 3, we know statement 3 is true because we've gotten there by a sequence of statements that we know are true. So we know that this abbreviated symbol is true. So all we can do with that is to unpack that symbol, write what it really means in an unabbreviated form. That's statement 4. So we use the definition of union. We unpack that definition in going from statement 3 to statement 4. And also realize that in our frame, our little mini direct proof frame, we had in statement triple asterisk, we had this defined expression, y is an element of B union C. Now that's an abbreviated symbol. We want to be able to say that that statement, triple asterisk, is true. Well, the only way to get to that point where we can say that that statement is true is if we have previously proven that what this thing really means is true. Well, what that statement really means is this. So that circled statement, 4 asterisks, needs to be there before the statement that we really want, statement triple asterisk. Before we can say that statement triple asterisk is true, we have to first prove statement 4 asterisk. So once we do that, once we prove that statement 4 asterisk is true, then we do what's called packing up the definition. We're packing up the definition of union. So the definition of union gets used 2 ways. We unpacked the definition of union in these 2 steps, and we packed up the definition of union in these 2 steps. Now let's think about what we've done so far. We've assembled 8 statements of the proof without having any choice about them. That's the idea of what I refer to as considering proof structure. For a lot of students, the idea of writing proofs is intimidating, with some mystery about how proofs are kind of conjured up. And it's true that sometimes there is a leap of inspiration that you have to have in order to complete a proof. But often, much of what happens in a proof is not mysterious. Some steps are inevitable. In particular, the frame of the proof, the beginning and the end, is often very formulaic. And the idea of unpacking and packing up definitions, that's also not mysterious. It's very formulaic. And so the result is that the mysterious part of the proof can be narrowed by considering proof structure. Let's go back up and look at what we have. We have now a proof that has a big chunk of the steps done, and we have only this gap in the middle that we have to bridge. So all of these 8 steps shown here are steps that were sort of inevitable. Now, in our proof, the gap that we must leap is from statement 4 to statement 4 asterisk. This gap. Notice that statement 4 is an OR statement. Statement 4 says y is an element of A or y is an element of C. That gives us a clue that the way to proceed is to use what's called proof by cases. So here is kind of a mysterious leap that we had to make the connection in order to do that leap. So the proof by cases unfolds this way. These steps get put in, and also some explanation gets put into our existing step. Remember earlier, we didn't know how we were going to justify statement 4 asterisk. Statement 4 asterisk, we just knew had to be there, justified somehow. Well, now we realize these statements have to go in that gap, and furthermore, this is how statement 4 asterisk gets proved. Now let's look at these statements in more detail. Statement 4, our OR statement, says either y is in A or y is in C. Of course, y could be in both of those. That's the inclusive OR. What you do in a proof by cases is you start by saying, well, suppose that y is in A. So you suppose that you're in the first case, and that's an assumption for a proof by cases. Then you somehow want to get to the thing that you were hoping to prove. The thing that we're hoping to prove is that y is in B or y is in C? Well, in this first case, we want to show that in that first case, y is in B or y is in C will be true. Well, we can do that in this first case, because if y is in A, then we can say that y is in B because A is a subset of B. So we use statement 1 in order to say that y is actually in B as well. And since y is in B, then we can say that y is in B or y is in C. That's just by, that should be statement 6 here, by 6. If y is in B, then we can certainly say that y is in B or y is in C is true. So we see that our goal, our statement that we wanted to prove is true. We can say that it is true in this case. That's the green case, case 1. Now let's consider the other case. The other possibility was that y was in C. So we say, suppose y is in C. So that's an assumption for proof by cases. Well, if y is in C, then we can certainly say that y is in B or y is in C by that statement 8. And so the thing that we are hoping to prove, y is in B or y is in C, is also true in this second case. So we have this green case and this red case, and they both end with the statement that y is in B or y is in C. So we can put in what we call the conclusion of cases. You say that, well, this blue statement is true because it's true in every case. That's the method of proof by cases. So this sequence of steps was bridging that mysterious gap in the middle of the proof. With that, we realize that we've closed the gap. We can number our statements 1 through 13. All the justifications are there. You can see that in this proof is the frame that was inevitable. These steps we didn't really have any choice about. And then the mysterious gap in the middle that we filled with that proof by cases. That's the end of that example, and that's the end of this video.